questions before we get into it? Okay. Okay, so last time we introduced this Langlands functor, for example, in the de Rham setting. And also in the Betty and et al. Settings. Well, maybe I should say restricted. And so I guess I want to start today by adding more structure into the story, or general features of the story. And so this is the theory of Eisenstein series, which we've seen mentioned a couple times already. So let me just do it briefly. So there's a functor we call I streak. Okay, so the setting is I'm going to take M, a Levy subgroup of G, and I'm going to take a parabolic P parabolic, of course, with Levy quotient M. And then the definition is that the functor of Eisenstein series from sheaves on bun M to sheaves on bun G is given by the formula P lower shriek Q upper star, where the notation is given by the diagram. It takes bun P down to bun M. So this is Q, this is P, and this goes down to bun G. And let me just make one remark. Well, let me make two remarks. So the first remark is that this functor of Eisenstein series is left adjoint to the functor of constant term, which by definition is goes the other way. And so I do P upper shriek and Q lower star. And then remark two is that in the de Rham setting, which, you know, people... okay, in the de Rham setting, this constant term star is sort of obviously defined in the sense that in the world of D-modules, you love upper shriek and lower star functors. Those are always sort of, those are the functors you have in the formalism. And part of the analysis of Eisenstein series just sort of the initial analysis of Eisenstein series by Braverman and Gatesgory implies that the left adjoint actually is defined here. So in other words, that the left adjoint to this functor exists. That's a yes or no question.
But you're not claiming that individually the P lower shriek and the Q upper star exist?
Right.
That the composition exists.
The composition exists.
Okay.
Yeah, it's like a slightly subtle statement. Yeah. Yeah. And the other, yeah, I guess if you, okay, if you think what the mechanism for it is, just to say a couple words, I don't know, in case it's helpful. So, okay, what are the issues? So first of all, you want this P lower shriek to exist. That, it doesn't, but like, that's one of the enemies. Right, exactly, you want it to. And so when, in the D module world, basically, so this is like a representable morphism. Basically, P lower shriek only really exists as a well-behaved functor if this morphism is proper. And so what you want to do is compactify this morphism, and there's a known way how to do that. It's the Strinfeld compactification. And so that gives you sort of control over the P lower shriek part. And then if you think what's happening, what you'll do is you'll take the constant sheaf on this bun P, and you'll push it forward to the Drinfeld compactification, which maps to both of these. And the assertion is that the resulting sheaf, so you shriek, push it forward. That's a good holonomic blah, blah, blah operation. And then the real content is that that object is ULA over this bun M. And so that's going to tell you that if you sort of do a shriek, pull back, tensor with that object, and then a star push forward, it's going to be the same as star pull back, tensor with it, and then shriek push forward. In particular, the latter is defined. The latter is the thing we wanted. So it's computed by this other formula that kind of manifestly makes sense.
When you say drum setting,
Yeah.
it includes also non-holonomic D-modules.
Absolutely, yeah.
So in that case, even lower sheet like along the margin might not be defined.
Exactly, yep. That's exactly the kind of thing that's exactly the kind of anxiety that's behind this comment. Yep. And that's why, like, this isn't some kind of general, well, the general axioms for this in the D module world will have to do with like if you wanted to say when does this kind of thing happen, I kind of just gave an answer out loud. So you can give some sort of general axiomatics, but I would say it's really the existence of this functor here is really sort of a feature of geometric representation theory in some sense, and not a feature of the like general theory of D modules. You can't just say this and have it exist. And yeah. And for what it's worth, this is actually really also reflected in the setting of étal sheaves and Betty sheaves. So, I mean, there are these formalisms of sort of functors given by kernels, and there's two different notions of functors given by kernels, and this functor is sort of obviously an upper star lower shriek kind of kernel, but the theorem is saying it's also an upper shriek lower star kind of kernel functor. So it sort of exists simultaneously in both worlds, if you like. So it's just to say that these sort of funny features of the D module setting, you can actually kind of imitate them in the Betty and étal settings, and this kind of assertion has already serious meaning, and if you kind of set up the formalism in a certain way. Okay, so what is the job of this functor in geometric Langlands? So this is kind of parabolic induction, is what you're supposed to think. So it's like we're trying to understand this category, and one of the things you're supposed to do in geometric in representation theory all the time is to understand something about G. You want to just get as much as you possibly can by parabolically inducing from M, and then the mystery always is kind of, so to say, the cuspidal part, which is the stuff that doesn't come by this kind of induction procedure. And so the theorem which I want to sort of at least outline the proof of is that the following diagram commutes. Well, okay, let me maybe hold off on that for just a moment. So there's a spectral counterpart, which is the following procedure. So I take so we did this already in some sense, but I just want to repeat it in a slightly different way. I said that it was provisional, and now I'm going to say it in a oops, it's a little graveyard of chalk down there. Okay. So there's a sort of parallel version here. Let me call this the Q check and P check for the moment. So well, okay. Let me just give a feeling for the. Okay, there are these two pictures which look formally very similar, and I want to say that the geometry is quite different. So, for example, every vector bundle admits many, many, many flags for a curve, on a curve. So if you can just find, for example, in the case of GL2, you can find you can find flags like where the degree of the subbundle is as negative as you want it to be, and so there's sort of this map is sort of highly surjective. In this case, this map is not at all surjective, so anything that's in the image is going to be a reducible local system. So, so the picture is formally the same, but the actual geometry, I just sort of want to highlight, is quite different. But so then we define, so I said this formula before, but I want to just repeat it now in the INDCO setting, because we did it in the quasi-co setting before, and I said it was provisional. So, so there's a functor I spec from here to here. And the formula is just more or less the same. So you pull back, and then you push forward. And let me kind of just remark here that this Q check is what's called quasi-smooth. So that implies that this Q check upper star exists in the INDCO world. So let me just say that the existence of upper star functors in the INDCO world, it works when you have finite toward amplitude. So I mentioned that during the first lecture. We saw that to sort of pull back coherent sheaves along the setting, I needed some finite Tor amplitude. Yeah, and maybe let me comment here that the fibers are sort of twisted versions of loxis NP, where NP is equal to the radical, well, the unipotent radical of P. Check, apparently. And basically all I want to say is that by design, like by the definition of this nilp on both sides, these functors really, like this functor really sends INDCO nilp here to INDCO nilp here. And so I remind that this map is proper, and this map is again this sort of quasi-smooth, just to have the geometry on the board. Yeah, which is parallel to the fact that this map is smooth and this map is not proper. And so what the theorem says that I'll try to say a couple of words about is the following diagram commutes. So so I can take, let me be in the D module setting for a second. The following diagram commutes, well, okay, it's a construction. So we really have to produce the data of a natural isomorphism. So this is a slightly sloppy way to say it, but okay. And then and similarly, and this is our Langlands functor for M. This is our Langlands functor for G. And similarly for the Betty and restricted settings. Yeah, so okay, so yeah, I want to comment on the meaning of this. So what is this saying? So like I guess like what does this spectral Eisenstein operation do? So you take an M-check local system, so think of like a semi-simple local system. I guess yeah. So it's some semi-simple local system, so think of some just like block diagonal matrices. And then you consider all the possible ways of lifting that semi-simple local system to a local system for the parabolic. So sort of all the possible, so to say, extensions, all the ways of filling that into upper triangular matrices that reproduce what you were looking at along the diagonal. And then you take the corresponding G-check local systems. So this is kind of a quite natural operation, I would say. It's also maybe exactly the kind of thing which is invisible in the classical Langlands program. So like in usual spectral theory, like how should I say, you only see like sort of Hecke eigenvalues are not able to distinguish like general local systems, general Galois parameters from their semi-simplifications. And so yeah. So these two are sort of say the same at the level of semi-simplifications by definition. So just a comment. Okay. Yeah, and so this is saying that operation of kind of, again, considering all the lifts to the parabolic and then integrating over those, saying that that's what corresponds, that's what this geometric Eisenstein series is doing. Is it's it's affecting that in on the automorphic side. Okay, questions?
So there's no comparison between the bump P side and the local system on P side.
That's right. That's the.
Or no, that's the question.
Yeah. That's the misleading thing that everyone always. It's extremely tempting to say that, and it's not how it works. Like you can just.
Is the functor also independent of the choice of the parabolic?
The functor is not independent of the choice of parabolic. There's So there's another operation you can do, which is called compactified Eisenstein series. And maybe I'll mumble some words about it at some point. And a like wrong but almost correct statement is that the compactified Eisenstein series functor corresponds to push forward from here to here. So that's just sort of like taking a semi-simple local system for the levy and considering it as a local system for G-check. That's off for like slightly subtle reasons from being correct, but it's kind of true generically over loc-sys, for example. And so when you're in the kind of regime where that's true, then you get the independence of the parabolic.
Can you also use intertwining operators to construct maybe natural transformations between the inductions from various parabolics?
Yes.
Yeah.
That's a kind of exactly one of the key points of this original Braverman-Gates-Gorey paper. They do exactly that. Well, I have the principal case in my head, but I think they I forget whether they in general like treat associated parabolics or only like conjugate parabolics, but I think probably that. Okay, I'm not sure. But anyway, yeah, a posteriori, all of those things are true. But they're true for that other form. Other questions? Okay, so Dustin asked me to say a couple words about how the proof of this diagram goes, so I'll kind of...
No, I didn't.
You did. It was at lunch like 2 days ago.
Yeah, but I didn't ask you to do it in your lecture. I just want
I thought you did. Oh,
to lecture on.
okay. Well, no, but in the first talk, you're right. You weren't at the first talk, but I told everyone just tell me wish lists, and I'll try to do the things. I don't have to do it.
When do you need the driven compactification in the funky side? Do you need to define the SSM functor or define the compactified SSM functor? You need to use the compactification. Or how does it like compatible with the spectral side? So you need to use the compactified SSM functor to have this diagram compute, or
No. Wait. Okay. Sorry. Maybe I should. Okay. First of all, I should say it commutes up to cohomological shifts and tensoring by line bundles. So there's slight subtleties there. So I'll just always, once and for all.
yeah, but at the top you need the Dreyfus compactification, right?
To do what?
To define that the P or shrink.
Well, I don't. So I would say you need the Drinfeld compactification to prove it exists, this functor. But see, I wrote down this constant term functor. So it's some functor from here to here, no Drinfeld compactification. And then it's a yes or no question. Does it have a left adjoint? It's a general categorical assertion. And then there's a question, how do you prove it has a left adjoint? So the theorem is, yes, it has a left adjoint, and the proof goes through the Drinfeld compactification, absolutely. And proofs, all the sort of proofs in this world go through the Drinfeld compactification in many ways. But in order to state the diagram, I don't need the Drinfeld compactification if you just accept that the left adjoint exists. Yeah. Does that answer your question? Yep. Yeah. Okay, maybe I'll. Okay, let me let me just say a couple words about how you prove something like this, but less than maybe I'd planned. So. Okay, so let me do the outline, and let me just assume for simplicity that P is equal to B and M is equal to T for convenience. It doesn't really make a serious difference. Well, it makes a serious difference at some points, but okay. So first, you reduce to showing the following diagram commutes. So it's sheaves on G, on M, on T, to T modules on G, and then here is quasi-colloxis T check. So far it's exactly the same diagram, and but then I'm going to put quasi-colloxis G check here, and I'm going to do this coarse functor. And you're basically reduced to this by definition of LG. I mean, you have to unwind a little bit the homological algebra and make sure certain things are bounded from below, but that's okay.
But I thought your motivation for in Coindel was that the bottom functor.
That the bottom what?
That the bottom functor was not going to work at the QCO level.
No.
No.
I mean, I'm literally just, so say applying this functor psi. Okay, the diagram does not commute if you, sorry. So, okay, what I'm trying to say, there's this functor psi that goes to QCO Luxus G check.
Because generally for a proper map. For
arbitrary push forwards, the push forwards are intertwined by this thing.
Okay, so yeah, the push forward still exists, but it's just doesn't commute with colimits anymore. Is that?
It does commute with colimits. It doesn't have a right adjoint that commutes with colimits.
Right adjoint. That's right. It doesn't have a right adjoint that commutes with colimits. So you can still talk about it. All right.
You can still talk about it, and the diagram's still supposed to commute. But let me say, you could have done a parallel thing here with constant terms. So if you went, so if you took, what I want to say is kind of the parallel thing for constant terms, you can't be as naive about it. Okay. Because if you take the constant sheaf here, you'll get non-zero constant terms when you go down to bun T. But if you apply the coarse Langlands functor, it goes to 0. Mm-hmm. And so that's a serious, the commutation with constant terms doesn't just reduce to this sort of picture, but the commutation with Eisenstein series does. Yeah. Where am I? I'm here. Okay, so first we're reduced to showing this. Okay, now, okay, so okay, what would I sort of, okay, let me mention something kind of, okay, so then you can sort of pass to right adjoints everywhere. No, I'm saying it wrong. Okay, let me say it. What am I trying to say? Sorry, just 1 second. I want to not screw this up too badly. Sorry. Confusing myself about. So, okay, so you pass to what's called the dual categories, and then you have to maybe have a little bit more input, but let me just ask you to believe me, the plausible assertion that then what you're reduced to showing is that the following diagram commutes. So I sort of just want to move the quasi-co-loxis g-check up to the left here. So this is going to be this constant term spectral, which is given by the right adjoint formula here. So this is q-check lower star, p-check upper star, or the sort of quasi-coherent version of it. So sometimes we write this. And then here, this is going down to d modules on G. This is my constant term star. And this is this d modules on T. And so what is this functor doing? So this is acting on this Poincare object. And let me just so I think it's I feel like I'm skipping some steps, but I just want to say that this is, kind of clearly the same level of difficulty as the statement over there. And so, so I would say maybe the main step. Well, there's sort of two main steps in this argument. So the first is calculate where O goes. And so what is this? So if you do the sort of upper circuit, or maybe I'll do the lower circuit first. So this circuit, so this is this part of my diagram, it sends it to constant term star of Poincare shriek. Clear? And then if you run this circuit, so what do we end up with? So we get this object Q star of O loxis B check. Well, but kind of like the Langlands dual to that. So if you like, this is what you get by acting on kind of the skyscraper sheaf at the trivial the trivial T bundle. So this is sort of unwinding what LT is. Well, or maybe better way to say this is kind of Q check lower star of O loxis P check. And then this is the Hecke action on the Poincare sheaf for T. and so what we want to do is produce an isomorphism between these two objects. So this needs sort of various geometric inputs. And I'll just try to give a little bit of a feeling for it. So, OK, so what's happening here? So we have this geometric expression, and this is some kind of sheaf that we want to understand. And the problem with it is that this Poincare sheaf is sort of defined with upper stars and lower shrieks, and this constant term is defined with upper shrieks and lower stars. And when you compose those kinds of functors, it's like it's a theorem how you calculate it. It's not just for, you can't just do like naive base change. And so so there's a theorem due to Drinfeld and Gatesgory, and it's this kind of second adjointness in this world. Bernstein style second adjointness, and it says that this constant term functor is equal to the sort of Schriek version of the constant term functor, but for the opposite parabolic. So here I take bun m, I take bun p minus, I take bun g, and I apply this sort of q minus, p minus, and then constant term Schriek is equal to this p minus upper star, q minus lower Schriek. Well, and again, in particular, this functor is well defined. In the D-module world. And kind of for different reasons than happened for the Eisenstein series. And so now you can calculate this constant term Schriek. Well, you can calculate this constant term star Poincare Schriek as constant term Schriek minus Poincare Schriek. And now this is something that can be calculated by base change. So I take this bun n with the omega, this map down to a1 by the exponential. And then I have kind of this map with the omega down to a bun g. And then I have this p going to bun b minus, and this q going down to bun t. And I'm just doing sort of upper stars and lower shrieks along this diagram. And so I can calculate this by base change. So what is this kind of, bun b minus? So what is this fiber product? So this fiber product, let's say for SL2, parametrizes the following sorts of data. So I have a point in this bun n omega, and then I also have a point in bun b. And I should say that these both give isomorphisms between the determinant of E and O, and those should give you the same isomorphism. So there are sort of these transverse maps that are kind of measuring how far apart these flags are from each other. Let me just make that remark. And again, sort of by the setup, these are actually dual maps. but yeah, up to this twist by omega, this is sort of a map to G mod, this is a map from the curve to G mod B minus mod n. So it's sort of a twisted notion of map like that. So there's an open inside of here where the two flags are in generic are generically on X transverse to each other. So this is sort of like saying there's this map from X to G mod B mod n, kind of twisted by some omega, maybe. That's the kind of data of a map here. And then I'm saying that this is supposed to, and there's a minus, and then here there's sort of this open point, which is n omega b minus mod n omega. And I want there to be some open u inside of X where this factors through this open point. And so this is called Zastava space. As far as I understand, Zastava is Croatian for flag, and it was named by Mirković, who's Croatian. And it's sort of a very nice geometric setup. So yeah. So okay. So in the example, this corresponds to the diagonal maps being non-zero. That's this sort of explicit open condition. And so you end up with this Zastava inside of this space. And so you do the following check. So basically, what am I doing? So I'm taking this exponential sheaf here, I'm pulling it back to this fiber product, and then I'm pushing forward to bun T. And you check that the sort of pull-push for this fiber product is the same as for Zastava. So this is somehow, let me just say, this is sort of it's part of, this is a familiar pattern in geometric representation theory where when you deal with some kind of Whittaker object and you try to compute something like a constant term for it, or just when you're playing with Whittaker things on kind of the flag variety, they really kind of only can see the open Brouhat cell. So for example, you can talk about Whittaker sheaves on the flag variety, and those are all supported on the open Brouhat cell. And this is kind of modeled on that sort of idea. And so then there's a little bit more geometry, which is that this Zastava space actually maps to some kind of space of divisors. So let me say div x for lambda check pos. So these are divisors on x valued in positive co-weights. Where positive co-weights means divisors of the form some ni alpha check I. So these are the simple co-roots. And of course, all of the ni's are greater than or equal to 0. So in other words, this is just a product over the nodes in the Dynkin diagram of symmetric powers of the. It's a disjoint union of products of symmetric powers with the indexes labeled by nodes of the Dynkin diagram. And then this is mapping down to Bun T, and the statement is that, nope, other way. The statement is that the Zastava space actually maps to this space of divisors. Again, the idea being you get a divisor from this cross map. It's the divisor of zeros of the map. And that's what your divisor will be, and sort of you can kind of clearly read off the data of like this L from the data of of that divisor, because this L dual, for example, will be omega of 1/2 twisted by the divisor. And then it turns out that this picture of Zastava over the space of divisors, this is actually all local on the curve. So it's not really a global statement anymore. So this is something which makes sense for, like, I can talk about the space of divisors for an affine curve. I can talk about the Zastava space for an affine curve. Sort of because everything for the Zastava space is trivialized on some open, nothing really, there's just some like bubbles around some finite set of points where all of the action happens. And so so all of a sudden, this sort of problem of global nature becomes a problem of local nature, and then you're really kind of, that's the sort of thing that I guess we're good at doing in geometric representation theory. And let me just comment that so the explicit calculation in this case, sort of on the Zastava space, was actually done in my thesis. Yeah, where again the methods very much are using compactified Eisenstein series and all these kinds of things, but that's what the answer is.
What is a compactified Eisenstein?
Let me not do it. Yeah, we can talk about it afterwards. Yeah. Again, it's okay. Do you know the Sternfeld compactification? You heard the definition. Okay, it gives you a correspondence between bun G and bun M, let's say. You just pull back, tensor by the IC sheaf up there, and then push forward. So that's a definition. Turns out this IC sheaf is pretty manageable, and kind of on the spectral side, this is much more like just, again, sort of restriction from, or it's just sort of like the push forward from locus M check to locus G check up to some, that's like a slightly a lie. You have to be a little bit careful about it, but that idea tends to make a lot of these calculations much simpler.
But then you can re-express U. So how is it used in practice? Is compactified? So you can re-express one through another, or?
Well, okay, it's kind of the following thing. So I guess I said the calculation was done, but here's some kind of object, which is like not completely trivial. If you sort of do the compactified Eisenstein series version instead, you basically get just O of locus T check. In other words, you just get the skyscraper sheaf at the origin. And so it's kind of a simpler object. And so you play those two things off of each other in order to...
Okay, so you can do these things to kind of compactify things in different ways, or no?
Yeah, that's a reasonable way to think about it. So it's just like the thing you have to calculate is sort of like there's some ways of moving between this Eisenstein series and this compactified Eisenstein series is sort of what you should think. There's some procedures, and again, it's sort of like there's some sort of amount of conservation of difficulty that happens in converting. Like if you have a problem about Eisenstein series, there's probably a corresponding problem about compactified Eisenstein series, and which are roughly equivalent. Yeah, I mean, like take that with a grain of salt, but it's roughly equivalent. And the problem about compactified Eisenstein series, the thing you have to calculate might just be easier. It might just be like this Poincare instead of, yeah.
Is there an analog of this second adjointness for like other elements of the file group?
I do not. I would say no. Yeah. Yeah. Of course, I would be happy to hear I was wrong in some sense, but yeah.
Could I also ask you to just say a couple of words about what these shifts and twists you were talking about are, or how they come in?
Sure. So let me just say one word about that. Oh, I lost it. Okay. So when I did this spectral Eisenstein series, there's Loxus P check mapping down to Loxus M check, and that's this quasi-smooth morphism. And so you have like upper star functor, but you also have an upper Schriek functor, which is the same up to tensoring by a line bundle. It's like that kind of issues.
So is it like, do you have to at some point extract the square root of this twist, or is it? I mean, how does it mean the diagram actually commutes if you do an upper Schriek instead of an upper star in your definition of Eisenstein series in the spectral setting, or what? Like I failed to see how that remark
Answers it?
Yeah.
Yes, I want to be careful because I didn't prepare the normalizations. Let's see if I can say. I would kind of say the following. So my experience with this stuff is that there are various diagrams you want to have commute in this whole story. So
I would like that one.
Yeah, you would like that one just to commute, but also you would also like this Poincare sheaf to just correspond to O, for example. But already there are sort of choices about what this Poincare sheaf is. So you push forward the constant sheaf, I said, in some kind of global setting. But there's also there's a natural functor from the local Whittaker category to D of Bun-G, which is some also version of Poincare series. And this version of the functor, it's going to send the unit object in rep G check or in the Whittaker category for the FN Grossmannian to basically the same Poincare sheaf, but there's a cohomological shift because it's not sensitive to the dimension of Bun N, which has the genus of the curve entering in, which is kind of the constant sheaf did. So you're gonna see something about maybe omega on Bun N versus the constant sheaf on Bun N entering in that setting. And so already kind of for what the Poincare sheaf is, it's a little bit defined up to cohomological shifts itself. But then, I would just say there are sort of these commuting diagrams you want about Whittaker coefficients, about Eisenstein series, about Kac-Moody localization, and each of them, it's hard to make the cohomological shifts and twists consistent across all three of them. And so when you simplify one of them, the other two pick up some kind of annoyances. That's the general problem. That's a technical point. So all of them have their little room for ambiguities, and it's a little bit yeah. Yeah, I mean, you see this also in this Benz v. Secularidis Venkatesh stuff, where there's sort of, I think, they have a little bit of a science around these, again, line bundles and cohomological shifts, sort of for each one of these relative Langlands settings or something. I think you kind of always see it. It has its own little obstructions in some way. At least that's what's in my hard about this stuff. Okay, so that was step 1. I guess I don't completely want to spell out step 2, but let me just kind of give a feeling for it. So what's the issue? So the issue is, okay, what you want to do is upgrade this diagram to be acted on everywhere by quasi-coev-Lhoxis G-check, so that just computing the diagram on the single object works. That doesn't, that's not quite sufficient here. So yeah, let me just say step 2 is so you refine the diagram above. So what you try and do is something kind of strictly harder than prove this diagram. Maybe we're supposed to call it partially enhanced, but so it turns out that there's a canonical way to upgrade the Eisenstein series functor to actually, so this was done by Braverman and Gatesgory. And so what they did is, so to say, they computed like the Hecke action on this Eis streak. So what you can do is you can run this Eisenstein constant term. Well, it's kind of, you can do it dually in both directions. But what they sort of did is you can say, OK, suppose I apply a Hecke functor on bun G and then take the constant term of that. What's the result going to be in terms of bun T? And kind of the diagram I was saying before, it doesn't like, kind of means the question doesn't quite make sense. Well, anyway, because the answer is not expressible purely in terms of bun. Maybe I should say it the other way. So if you do this Eisenstein series operation from here to here, you can do a Hecke operator for Also, okay, so you can try to ask, let me say it the way I was saying it. So you say this constant term operation, and you want to sort of formulate the question of what happens if you apply a Hecke functor on bun G and then take the constant term down to bun T. And there's a classical answer for this in automorphic forms, but well, if you believe the philosophy, it doesn't quite, okay, like part of where the philosophy came from was exactly this analysis, and what they said is that there are somehow some extra symmetries that actually any object of whenever you apply constant terms, it carries some sort of extra symmetries. It has an action basically of the object I erased of sort of functions on this Lhoxis B check, and so that's sufficient to give an upgrade to this functor, and this is sort of by design quasi-coev-Lhoxis G-check linear. And so then you try to prove that this diagram commutes, but to do that, you just need to know where O goes. So, because now it's a diagram of quasi-coev-Lhoxis G-check module categories. Okay, so that was the sort of outline of the argument. Questions? Okay. Oh, it was like I didn't ever really need it. Well, okay, I guess there's a couple points. So one is what's done in my thesis is for B. It was just so and the corresponding calculation in the case of general parabolics was done in a recent paper of Hayash and Feergman. I guess even in some sense all of this theory was really only done by Braverman and Gates-Gurry originally. Like that's the sort of original sin. They did it in the case of the Borel. And Feergman and Hayash a very nice paper sort of reinterpreting a lot of these things, but also extending to the general parabolic setting. And so, and they have an alternative way of doing this calculation, but they also reduce the corresponding calculation for parabolics to the Borel case. You have both things in their paper. But also, it's just to kind of slightly simplify the discussion. So, like, where the Zastava space lives, it's a little bit more complicated. It's some sort of positive Hecke modifications for M instead of like the space of divisors, of effective divisors, is kind of like for GM, it's like two line bundles. One's embedded into the. It's like maybe O is embedded into some other line bundle. That's one way to think about the space of divisors, and what appears as like the base for this Zastava space is some sort of Hecke modifications for the Levy, so it's just a slightly more complicated story. But yeah, no serious, super serious points. Other questions?
So it's a map from quasi-core of LST briefly, because I think that this is the map for the upper side.
Yeah, like here?
Yeah.
Yeah, that's right.
So that one on the right that you didn't write, that's automatically mutated. You said it refines the diagonal method.
Yeah, okay, so.
Yeah, I mean, on the right that's somehow the missing part.
Wait.
You think, it seems to me that, well, tensor should be like some push factor. Here it's kind of like on the sliding right.
Okay, so what this is explicitly is you can take this Q. Okay, so maybe I should have said that loxis B check over loxis T check. Okay, so I said the fibers are sort of like loxis N check, yeah? And that's kind of a quasi-affine stack. So it has, it's quasi-coherent sheaves are the same as modules over its global functions. So this is actually turns out to be modules over this object inside of quasi-co of, well, inside of D of bun T. So like this category is modules over this inside of here. That's kind of the relative version of what I was just mumbling. And so what this is really saying is like this algebra acts on anything arising as constant terms. And so, yeah, so you kind of, I guess I more properly should have said like you do step 1 and then you do step 2 and then you do this additional step 3, which is to make sure that the two actions you saw here are the same. So there's kind of an obvious action on the thing I wrote down, and you have to make sure that that's the one you got when you compare with step 1 and step 2. So.
There's also a notion of enhanced constant term that's purely used, like their IGB stuff.
Yeah.
Are they the same stuff?
Yeah, that's why there's this P here instead. So this is partially enhanced. Yeah. So like so you can sort of imagine like trying to factor this Eisenstein series. Okay, what the enhanced Eisenstein series? Okay, that whole story is about kind of changing the target of what sort of constant terms you take. So here I was saying this partially enhanced thing goes through loxis B check instead of loxis T check. The like fully enhanced one goes through the formal completion of loxis B check. The formal completion of loxis G check along loxis B check. So the sort of space which is physically the same as locus B check, but infinitesimally the same as locus G check. So that's what it does. I think the general philosophy is that like this partially enhanced thing can be slightly more elementary to set up, at least in the global setting. It's somehow more it's a little bit more elementary, and it's a little bit easier to wrap your head around, and it's also sufficient for all applications. However, to really kind of have at various points in the theory, it's convenient to really have local analogs of all of these objects, and the local analogs are they're like simpler in some regards and more complex in other regards. And when you're dealing with them, it's basically as hard to do the partially enhanced version as to do the fully enhanced version. There's not like actually major simplifications that come there. So we dealt with all of this IGB stuff in the paper. Well, other questions?
So this work, Breverman, that's where it shows that this square is commutative together with a linear structure.
No, I would say what they do is they construct this functor, and then I'm kind of explaining how to. So step 2 is kind of to first say that you're allowed to talk about this object, and now you get a simpler problem than the one that's above, formally simpler problem, which is to show the commutativity of this diagram.
So this diagram is automatically commutative. Linear. All functors are.
All functors are linear now.
Yeah. Exactly. Okay. And you just need to check it.
Then you just need to check it commutes on one object, and then you sort of refine slightly that calculation. From one. Yeah. Other questions? Okay, so I want to maybe make one comment on what I think of as what I see as the simplest point of view on geometric Langlands conjectures. So problems. In terms of like what kind of thing are you supposed to do? So this is it's not exactly the way the argument's given. I don't know that like Dennis would cosine onto this point of view. So take that with a that's why I'm putting my name here, or whatever. But I just sort of want to say a little bit how I think these things should go. So I want to give a little bit of development just to give you a sense for like what kinds of things do you need to prove. And the kinds of things we end up proving are often more sophisticated than what I'm saying and maybe eradicate certain points. But I still want to maybe just share this. So the okay, so there's a sort of basic definition, or there's a kind of this. Okay, no, let me first give a theorem, which is due to myself and Joachim, and let me comment that this is a little bit the coarse version. And I'll say something about more refined version later. And so it says that this category of D modules on G is compactly generated by two classes of objects. So the first is, okay, so you take this Poincare sheaf and then you apply Hecke functors to it. And then you can take a compact object here. And the second thing is you apply compactified Eisenstein series to the same sorts of objects. Or you can just say Eisenstein. Maybe in practice, it's just as easy to say you take Eisenstein series applied to a compact object for a proper parabolic. So this is a more refined statement than this, maybe. But it's basically applying one. You just get this from this by induction. But I want to say in practice, you sort of can view everything as coming either from Eisenstein series or from this Poincare sheaf. And yeah, this is a theorem I talked about in Paris a few years ago, and so I'm not going to do it again. But yeah, so it's, again, we've sort of discussed two classes of objects inside of sheaves on bund G so far, and this is saying that these two classes together suffice. And it's a, let me say that this is a somewhat like subtle theorem. So for example, like it's really sort of more naturally proved for this Sheaves-Nilp category in a lot of ways. And then you use this kind of equivalence principle to deduce this version of the assertion. Well, the hard thing isn't that these are compact. The hard thing is that they generate.
Could you comment on what this looks like on the spectral side?
Absolutely. So this is like colored chalk. So this is like saying take a perfect complex on Loxus G check, tensor with O. That's like perfect complexes. Is it okay?
Yeah.
And then this is like I's spec of perfect complexes.
Like all, basically all, okay, the singularities are concentrated at the boundary.
So in my first talk, the way I defined INCO-NULP was just to say apply I spec to perfect complexes for all levies.
Okay. All right.
So in classical Langlands, is there, maybe, sorry, I didn't want to interrupt.
Yeah. Okay. Let me just finish the statement. So just for context or whatever. So there's this kind of maybe general subtle notion due to Rankin and Gatesgory of coherent singular support. Very lovely theory, lots of amazing ideas there. But one of the real upshots, one of the main theorems from their first paper about this stuff is that, like, I mean, it's a very geometric theorem, but what it says in this example is that INCO-NULP is compactly generated by I spec of perfect complexes. Sort of the idea is that, yeah. So if you have like a nilpotent endomorphism that sort of always like gives the flag. Exactly. Yep. Yeah.
Yeah.
I wanted to ask what is the classical Langlands envelope of this theorem, or if there is one?
I do not know how to.
Because basically would say that all hospital forms can be expressed to something function, or how should I think of this via some operators which are ruled out of features?
Okay, I mean, it's a digression. So for me, like, there's this Hitchin fibration, yeah, and so generically over the Hitchin base, okay, there's this Hitchin fibration and it has a section, and sort of the structure sheaf of that section is what corresponds to this Poincare sheaf. At least generically, the fibers are like abelian varieties, and sort of translations by those abelian varieties, and then this Poincare sheaf corresponds to sort of like the unit section of those abelian varieties. And these Hecke operators correspond to translations along the abelian variety using the group structure. And so
On the fiber. Okay.
on the fiber. And so this is sort of roughly saying that you know, you get everything just by starting with delta at 1 and then translating using convolutions on a group. And completely ignores the Eisenstein part of it, but that's because, I don't know, we were working away from the bad locus, but also I don't.
So you mean that's how I should think about this result rather? This kind of picture doesn't have a version, like classical.
I don't know like exactly what category to take.
So maybe on the level of functions there is an analogous statement. Maybe I think some integrals. Hecke operators, maybe for
Okay, so for GLN, there's a corresponding statement, which is that if you have like a cuspidal automorphic form, then it has some non-zero Whittaker coefficients.
Okay.
So that's what the corresponding statement is. That statement is false for general reductive groups, but in the geometric setting, it still holds.
But you can say that any generic L packet that is conjectural contains a generic representation. And any cuspidal L packet assumed should be generic, right?
Yes, I mean that's.
So in other words, this Poincare series sees all the cuspidal things, all cuspidal L packets, and all that remains as always is the Eisenstein series and the residuals. Is it a classical interpretation of this theorem?
That is a good classical interpretation of the theorem, and you can sort of imagine. Yeah, and I guess part of that interpretation is that what we say is that in geometric Langlands there are no L packets. So that's one of the mottos which is reflected here. So that extra bit of analysis.
So L packets is a way to regroup kind of all automorphic form, and then in each
There are
packet
some
there
automatic
should be
forms
some.
which go to the same kind of representations. These are the L
Okay.
packets.
So the statement is that there is a representative for each. Sorry, there is an element in this L packet for which the Whittaker coefficient will be non-zero. Or
So if the lift GLM is generic, it means that this conjectural in general, one of the elements of the L packet is generic in the Gopi strategy.
And exactly one, in fact, is the general assertion. Yeah, I mean L packets are like not GLN phenomenon also. But like, as far as I understand, in this local Farg-Schulze setting, there's sort of all of these extra, like in the setting of p-adic groups, now there's all of these like Hecke operators, which are sort of new symmetries of in some sense, the category of representations of the p-adic group, in fact, something larger. And these let you move within the L packet. And so this is kind of, you can also think of it as reflecting that idea that L packets were really just a manifestation of a symmetry that we didn't know how to articulate before. And yeah. Oh, I'm going to do this one. What was that? It's exactly the same, just you put the nulp. But the proof is that basically, like, again, we did all of these things for like, let's see. So at least the way we did it, we really worked in this Sheaves-Nilp setting and used input from topology and also used input from Lie algebras, so like sort of de Rham theory. And so I would say we sort of worked in this setting that touches both de Rham and Betty of Sheaves-Nilp, and then used this kind of equivalence principle I said yesterday to deduce theorems about arbitrary D modules, but just as well about arbitrary Sheaves-Nilp.
Did this paper of Nadler and was it Taylor?
Taylor.
Did they prove this directly in the Betty setting, or was that a different aspect of your work that they proved?
Different aspect.
Okay.
So I guess one of the features is that if you take this Whittaker coefficient functor from Sheaves-Nilp to Vecht, then there's kind of a few statements. So on this Sheaves-Nilp category, it's T exact, and it commutes with Verdier duality. And moreover, like if you start with a like concrete perverse sheaf or something, now you get like a vector space. It has some dimension, and that dimension turns out to be the order of the characteristic cycle at some point. And so so we sort of gave a little bit ad hoc proof of that, and they gave a very nice geometric proof of it. Yeah. So this is the idea that these Whittaker coefficients on Sheaves-Nilp are like a microstock. And that was sort of essential to this argument because this gives you kind of a different way of thinking. Like the hard part is like suppose you have like a cuspidal sheaf, then you want to show that it has some non-zero Whittaker coefficients, and this really translates that into a problem in geometry. So it's like you need to say that up to dealing with Hecke functors, you can make a certain character, like the characteristic cycle at some point non-zero, essentially, and that was what the rest of the argument was about, if that makes sense. Yeah, but Jeremy Kaler has some improvements to this now also that work. Like the part where we did Lie algebras, I think he can do with modular coefficients now and things like that. So they're nice development since then. Yeah. Okay, so these are kind of the generators, and then our goal is to understand what happens to these generators. So let me give a quick definition. So I'm going to call AG. So it's a certain quasi-coherent sheaf in Loxis G check, and this is by definition LG of this Poincare sheaf, or LG course. And this is an important object in the theory, so let me sort of unwind this. So I can think about this quasi-co of Loxis G check, again, is acting on this category of D modules on G. Let's say, well, I guess now I'm sort of in the de Rham setting. And if you think what this so in particular, that implies that D modules on Bun G is actually enriched over quasi-co of Loxis G check. So whenever you have a monoidal category and a module category, assuming certain representability, that's always true by adjoint functor theorem here, this category becomes enriched over this category. And so I can form the internal endomorphisms. Well, basically this LG course was more or less designed to be the sort of internal endomorphisms from the Poincare sheaf. And so what that tells you is that this AG is the kind of internal endomorphisms. I should maybe put quasi-co Loxis G check of this Poincare sheaf. and so what we see, first of all, is that this AG is really an associative algebra in this symmetric monoidal category. It receives a map let's say epsilon from O loxis, let's go eta, to this AG. So this is the unit map for the algebra structure. And no, four down. And if I sort of want to sort of think concretely about what this AG is, so first, if I want to compute, let's say, the global sections of AG as a sheaf, so this is Ham from O loxis G check into these internal endomorphisms of the Poincare sheaf. And so what is that? That's just Ham from, it's just endomorphisms of the Poincare sheaf itself. Or if I wanted to compute maybe global sections of, like, let's say one of those evaluation bundles, the kind of thing I might want to compute, so sort of by that duality game, I'm led to consider objects like this, or again, maybe sort of integrals of objects like this. And this I can compute in more or less the same way. So this is going to be, what do I want to say? Like, that's, again, Ham from O into this EVX tensor with these internal endomorphisms. And then that's just Ham from the Poincare sheaf to into this like TVX acting on the Poincare sheaf itself.
Sorry, Sam, I'm I guess a bit confused. So this LG of Poincare is supposed to be LG, not course, is supposed to be the structure sheaf, right?
Yeah.
Okay, so then this is something that maps this. Wait, which so what if? So I feel like this unit map should be pretty close to an isomorphism.
Yeah. Okay. Expect eta is an isomorphism. Yep. Yeah. Okay, so I want to say the main work is to show that eta is an isomorphism. Yeah, maybe it buried the lead. That's right. But yeah, so
you were saying all this is really important algebra objects.
Yeah.
Kind of funny not to say that it's just the structure sheaf.
This is the main work you have to do in this business is compute this, and I'm trying to say what kinds of things are you trying to do, and like what data is here in this AG if you want to unwind it, yeah, like so just to give a sense for it, trying to say like what is this object concretely? It's sort of something that like. Okay, I should think about by this duality game where I tensor by sheaves and then take global sections. Like that's what determines a sheaf on quasi-colloxis. And I'm saying what that really does is compute Whittaker coefficients of Hecke operators applied to the Poincare sheaf. And some people know there's this Kesselman-Schleicher formula that tells you pretty explicitly what this object is. It's some other kind of Poincare sheaf. But actually, sort of, what you see on the spectral side is a little inexplicit here, and what you see on the geometric side is also pretty inexplicit. And so it's not a priori super easy to compare the two things. Yeah, and so I want to indicate the following claim. So suppose you know that eta is an isomorphism. So then the geometric Langlands conjecture follows. It's a lot of rain. Okay, so this uses some ingredients we didn't give yet. But maybe I'll still just try to indicate. So let's take this category of D modules on G, and then I'm going to write temp here, and this is going to be the category of D modules on Bun G modulo the kernel of LG course. And the sort of more refined version of our theorem says that this category has a local description. In terms of the sort of Hecke action on a DMod on Bun G, where this is now the derived Hecke category. And this is for any choice of point. So a priori, this is some huge, very subtle business about like global Whittaker coefficients of some automorphic sheaves. But I'm saying actually you can just choose a point, consider the Hecke action based at that point, do some homological algebra considerations, and that's going to that's going to tell you exactly which sheaves were in the kernel of this functor. And moreover, let me just say there's sort of a lot that's known about dealing with this spherical Hecke category. And so this kind of makes checking properties about things in this, it makes this kernel feel much more explicit. It gives you a number of tools for proving things about it. For example, that's where this theorem comes from, is you check that this sort of local condition is incompatible with being cuspidal. Just one point. You choose any point at all. Yeah, it's a purely local property.
So is this also realized as a subcategory of the?
Yes. Yep. Yeah. So again, maybe not a priori obvious from the definition, but it's a quotient, but the quotient has a left adjoint, which is fully faithful.
This is what's supposed to correspond to Q column boxes.
Exactly. Yep. Yep. And so then, using this local description plus properties of what's called miraculous duality. So this is something which is due to Drinfeld and Gates-Gorey. You prove the following, that these D modules on G, and then I take the compact ones, and then I embed this into D modules on bun G, and then project onto this tempered category. Prove that this is fully faithful. Yeah, maybe also for your question, it's worth saying that if I think of this as a subcategory, then the Poincare sheaf is in there. The Poincare sheaf is tempered, just not a surprise. But again, follows from this. Basically, I want to say this definition is like the worst possible definition for checking anything, and the explicit description is the good one. And what the theorem should really be thought of as saying is you define this locally, and then we say that it has this description, that it corresponds to this global Whittaker coefficients thing. Yeah, but if you think of it as a subcategory, it's exactly the subcategory you get from these kinds of objects. So that's maybe again, another equivalent picture. Nope. Okay, so then you get the following picture. So there's this sort of category of sheaves on bun G that's tempered. This has some version of this LG sort of tempered. So this, this functor, well, is rigged. Okay, this goes to quasi-coev loxus G check. And this is my coarse functor. So I have this functor from here to here. And what do I want to say? So this this LG temp has a left adjoint. Which is sort of, again, acting on this acting on this Poincare shriek again, which I should emphasize is the reason this works is because the Poincare sheaf is tempered. If I think of this as a subcategory. And also this LG temp is a conservative by the, so it sends, the only objects it sends to 0 are 0. And so this is by it's a FR result. And so the upshot is that this category of tempered D modules, the sort of job of this AG was that this is equivalent to these AG modules inside of quasi-coev loxus G check. So this is what Barbeck gives you. It's sort of simplified version of Barbeck in this setting tells you this exact theorem, and so that implies that if eta is an equivalence, then that implies that LG temp is an equivalence. And so then you get the following picture. So you take this D modules on bun G, which is compact. This now embeds into this. Wait, did I say this? Yeah. This embeds into this category of D modules on bun G, tempered. This is now equivalent to quasi-coev Loxus G check. And so we end up with an embedding here. And you can ask, what's the essential image? And the essential image, basically by design, is LG. Well, let me take a little more space. So in fact, we already kind of know. So it's like we say Karubi generated. Well, don't even really need to say Karubi here. It's fully faithful or generated. So it's just basically okay. Karubi generated by the following objects. So there's this LG course of these objects, Poincare Schriek. And so this is the same as this spectral localization of V tensor with O, because it's because I'm assuming that AG is equal to O. Here, let me put it as AG, and then this is log spec of V. So in other words, these are objects which are just sort of in perf of Loxus G check. It's exactly the class of objects I get in this way. And then I have these Eisenstein series of compacts, and I apply this functor here. But I said that this is some kind of spectral Eisenstein series of compacts, well, LG for M, LM of these compacts. And so, well, this is just sort of I spec of this co-nilp of Loxus M check. And so all of these together imply that the image is exactly this co-nilp. And so, kind of, so one way you can imagine this story is that I would say, like, I think historically what happened is that Valenson and Drinfeld said that D modules on bun G should be pretty close to quasi-coherent sheaves on Loxus G check. They understood that it was true for a torus, and I think that they understood at some point that if you try to start thinking about natural compatibilities of this diagram, it starts looking a little bit weird away from irreducible local systems. And then Arinkin and Gatesgory explained that you can replace this quasi-co-Loxus G check by this bigger category int co-nilp. And I guess I want to say that you could have also imagined an alternative history where instead they said that you should, well, they kind of did say this also, but that you could shrink the category on the left to these tempered objects and then say that that's equivalent on the nose to quasi-coev Loxus G check. So that's tempered geometric Langlands. And the tempered geometric Langlands, there's sort of at least like in order to prove it, you don't need to say any words about Eisenstein series. But then the kind of first hour of the talk about Eisenstein series was explaining that you can reconstruct the thing we call the geometric Langlands conjecture from the tempered version plus compatibility with Eisenstein series. Okay, so I wanted to explain that stuff. Questions?
So just one question. So in the data setting, you have some difficulty in proving that you can reach any local.
Yeah.
But how? I mean, can I already see something? I mean, here in this picture. I mean, because I don't know. And you don't have this problem in the D-module setting. So is this already visible in what you told us today?
It's not visible in what I've told you today. Yeah, I think if I had 20 minutes, I would be able to explain that, but maybe I'll put it off until Monday. I want to explain kind of the miracles of the de Rham situation. Exactly. But so far, this outline, like, you can take it to the bank or whatever. Anytime you want to prove geometric Langlands, like, this is, in any given form, I kind of claim that this is more or less what the sort of problem is that the most important thing is to prove that this O is equal to this AG. That's the main content of the equivalence, and then there's compatibilities with various operations you might do, which are sort of additional wrinkles you can put on it. But you should think of that as as the content. And yeah, I guess I want to okay, maybe let me make one comment about that. So I was saying, like, in order to probe this AG, again, the content is computing these sorts of endomorphisms, right? Okay, I'll leverage that into a discussion, which will be useful for later. Sorry, I'm just thinking what I want to say. So, so let me do a kind of sample calculation. So what I want to claim, and this is going to be really in the de Rham setting, and then we'll discuss that, is that the global sections of this AG are just scalars. So for me, global sections is always R gamma. And let me say that this is if the genus of the curve is at least 2, and the group G is adjoint. Slightly simplifies. You can do the calculation in the non-adjoint case also, but yeah. And so this is saying something about, like, probing this AG. So okay, I guess I want to make a So here's the so here's basically what happens. So let me give the outline. So okay, so this group T acts on this Banan omega. That was just built into the definition. So any twisted version of Banan carries an action of T, and this Poincare sheaf actually has a description, which is sort of follows from sort of some standard kind of properties of exponential sheaves related to a formula I wrote yesterday, this Kirillov model. Okay, so let me say this this bun n omega with the circle on top is the locus where the character is non-zero. So remember, I have this character psi, which maps down to a1, and I just take the locus where it's non-zero. And then the statement is that this Poincare sheaf is actually always equal to the following thing. So it's J1 lower shriek of the constant sheaf, J1 lower star of the constant sheaf, followed by J2 lower shriek. This is just so if you think what's happening, you should take the exponential sheaf here, and then you sort of first shriek push it forward down to this space, and then shriek push it forward down to this space. And I'm saying when you do that shriek push forward, you're averaging with respect to the torus here. What you'll end up with is actually the star extension of the constant sheaf. And
so this, for example, makes sense in the Betty setting as well.
Yep. Yeah, and it's just as true in the Betty setting.
Well, you can have an exponential sheaf in the Betty setting. You didn't really explain what the
Yeah, I mean, this is kind of the definition. I mean, this would almost be the definition in the phrasing. Yeah. If the group is not adjoint, then you also see some other local systems with finite order monodromy, but yeah. Okay, so now when the genus is at least 2, this bun n omega mod t, well, it's contained inside of bun b with some sort of fixed degree. I guess the degree is what, row check times 2g minus 2, which is contained inside of bun g. And this turns out to be actually a locally closed embedding. So it's a harder Narasimhan stratum. No, okay, so this is kind of closed. So the way this is working is like this maps down to point mod t, which embeds into bun t, and this is closed. And there's a point here, and this bun n omega goes here. This kind of why t acts in some sense is because of this square.
B is n, t semi-direct product n. Yeah.
Yeah, so this part is just a closed embedding. And so when I need to compute the endomorphisms of this Poincare sheaf, so that's going to imply that the endomorphisms of this Poincare sheaf are just the endomorphisms kind of the first step, the J1 lower star of the constant sheaf, which itself, that was an open embedding. So this is just endomorphisms of the constant sheaf on this bun n omega mod t. Oh, I said closed, but of course it's locally closed. No, that step is closed. That's locally closed. Phew. Okay, so now let's unwind what this is. So okay, I guess let me sort of kind of do an example for a second. So suppose that my group is PGL2. So then this bun n omega I explained was kind of R gamma of x with coefficients in omega with a shift by 1. And so this is some A1. So that's sort of my H1 omega times some unipotent gerb, so some copy of BGA. And then inside of here I have my so product of BGAs. Inside of here, so that's coming from the H0 of the curve, but it doesn't affect the endomorphisms of sheaves in any way. It doesn't affect the sort of topology. So this bun n omega with the circle, so I'll just kind of contract that gerb and just imagine I was working with this space instead. Now this bun n omega circ, this corresponds exactly to A1 minus 0. And my torus x, so this is just a copy of GM in this case, and this x simply transitively. In general, up to BGAs, the way this bun n omega is going to look is that it's just a product of copies of H1 of the curve, product of copies of what am I trying to say? A product of copies of A1 up to BGAs. Oops, that's what I wrote. So kind of, and so this is just like product over the nodes of the Dynkin diagram. Oh God, I made a mistake here. Did I? Just a second. Sorry. This is sorry. I should have said this is actually the locus where each of the psi i's are non-zero. Sorry. And so now this bun n omega, it corresponds just to the product of copies of A1 minus 0. And again, it's exactly the same picture. There's this torus which acts simply transitively here. And so what I see is that when I compute the endomorphisms of this Poincare sheaf, I just actually get scalars. That was it. It was like the cohomology of a point is all that entered in. And so you can just do this calculation. It's like, of course, you can see I'm using kind of many special features. I'm using that the group is adjoint, which is not a serious point here. I'm using that the genus is at least 2, which is, I would say, a serious point here. For example, it's I guess not true in low genus. And but you know, it's like.
Wait, but where are you using that you're in the Durand setting?
Okay, that's exactly the point I want to make. I didn't use that I was in the Durand setting. But this calculation is irrelevant in the Betty setting, because what you needed to compute was actually, like, really this AG is going to be this Poincare Schriek NULP.
Oh, I see.
And so that object, what I would expect, so so like, at least a posteriori, after geometric Langlands, this corresponds to saying that it's again R gamma of locus G check. So this is some simply connected group, and the genus is still at least 2. Coefficients in O is just scalars. I'm saying that there are no non-constant functions on the moduli space of de Rham local systems. And that's very, very special to the de Rham setting, because normally you just take a loop, you take an element of the fundamental group, and you take traces in some representations. You get many, many functions. So the Betti moduli space is it's almost affine. It's affine Mata reductive group. And so it has many, many, many functions. Well, I just told you a bunch of them. And so the simplicity of this calculation, it's really, really a genuine feature of the de Rham setting. And so for me, this is one of the places where the de Rham setting is really essential. It's like in my in my mind, it's kind of like trying to do Fourier inversion or something. So you kind of want to say that when you integrate all the characters, you get the Dirac delta at 1. and this is like some very baby version of that kind of assertion. Is like
This is the baby version?
Okay, in this setting, you need more complicated assertions, but yeah, yeah. Well, it's some. See this AG. It's something like. It's some sheaf over this moduli space of local systems, and you're trying to probe its size, right? And so at every local system, it has some fiber, and that fiber is very hard to control. That fiber is sort of like the algebra that controls the Hecke eigensheaves for the given local system. And so, like, what are you going to do with that? There's nothing you can say about it. But I'm saying that there is something you can say, which is that if you sort of integrate over all of those fibers, then you just get a one-dimensional vector space. And so that's useful. And yeah, it's so small, but yeah. And so it lets you kind of probe these multiplicity problems. Ultimately, this is responsible for the fact that like the fiber at every point is non-zero, and also that the fiber at every point is one-dimensional, which is the thing you're trying to show. Well, one-dimensional implies non-zero, but that's for your question. It's kind of, yeah. So we'll talk more about it next time. So, I went over. Sorry about that, but yeah, thank you.
How to understand this convergence description, local description, why does it depend on the point?
Why doesn't it depend on the point? So
But it's also equivalent to some global. I don't know.
okay, so you can. So I mean, here for me is like the most intuitive explanation. So there's some Hecke functor you can define at the point that checks are you tempered at the point or not. Yeah, so it's some Hecke functor, but it's in the derived.
So the local condition is something like the action of derived Hecke category factors through quasi.
Yes. Yep. But so.
Which is the Hecke operator and the constant. No, sorry.
It's not exactly. Yeah, you're thinking of GL2.
No, but what is the Hecke operator I need to take to check?
Take the unit object, project it down to quasico, and then project it back or embed it back into intco.
Oh, okay.
that'll map to the unit object, and then you take the kernel of that map, something like that. And so if that kernel acts by 0, then the other map was an isomorphism, and that's the same as the condition you said. So in other words, there's some stupid object you can write down in the derived Hecke category.
That homology of G is in the one person.
I think it's a little more. Okay, let's yeah. But it's something. It has some description. I just want it doesn't matter what it is. It's some Hecke operator, some object of the derived Hecke category that that determines whether or not you were like its vanishing on your object is the same as temperedness of the object. Yes. And moreover, this description of this object is sort of manifestly independent of the point. Yeah, it sort of fits into some family of Hecke operators over X, which is locally constant in X, locally constant in the point. And then you, for example, on the Sheaves-Nilp category, if it's going to map you into Sheaves-Nilp tensor this lease on X thing. And but therefore, if it vanished at one point, it vanished everywhere. So that's basically the argument. And then you can reduce to the Sheaves-Nilp setting.